Good day everyone! I am Jhon Mercado, and in this video, we will be discussing or presenting our laboratory experiment all about redwood viscometer. So first, let's take an overview on the contents of this presentation. So in this presentation, we have the theory applied in this laboratory experiment, their objectives, the materials or reagents, the procedure, the simulation process, the observation and calculations, as well as some safety reminders. So in this laboratory experiment, we applied the concept of viscosity. So what is viscosity? Viscosity is the property of fluid by virtue of which a layer of fluid offers resistance to flow over other layers of fluid. Viscosity is the property of fluid which determines its resistance to shearing stresses. It is also the measurement of internal fluid friction which causes resistance to flow. We also have here the two types of viscosity. First, the dynamic viscosity, which is defined as the shear stress required to produce unit rate of shear strain. SI unit is Newton second per meter squared, CGS unit is PWA, where 1 Newton second per meter squared is equal to 10 PWA. For the kinematic viscosity, it is defined as the ratio of dynamic viscosity to density of fluid.
So the objectives of our laboratory experiment is first to familiarize with the redwood viscometer instrument. Second, to determine kinematic viscosity of a given sample fluids at different temperature using redwood viscometer. And the third one and the last one is to plot the variation of the redwood seconds and kinematic viscosity with the temperature. So the materials to be used in the simulation are first the redwood viscometer 1, second the stopwatch, the third one is the thermometer, measuring flask, and the fluids to be used are engine oil and glycerol.
For the procedures, first, click on the drop-down list to select fluid. Next, click on the drop-down list to select temperature. Third, after selecting the fluid and temperature, click on the lift button. The flow of fluid will start. Fourth, observe the rise in level of fluid in the container and click on stop button when the fluid reaches the 50 cc mark. Fifth, now click on the reset button to reset the setup. Sixth, again, select the next temperature and repeat the procedure for all remaining temperatures. Seventh, after performing the same procedure for all the readings, select the next fluid from the drop-down menu. 8. Repeat the procedure for the selected fluid and various temperatures. 9th. Observe the variation in kinematic viscosity with change in temperature. 10th. Click on the plot button to plot the comparative graph for both fluids. And last, compare the graph between kinematic viscosity versus temperature.
So, good day everyone. We'll now proceed to the simulation of the viscometer using this virtual lab. But first, we have to answer these two questions in order to proceed the simulator itself or the simulation process. First question, shear stress required to produce unit rate of shear strain is dynamic viscosity. Let's see. Okay. Next, Newton's law of viscosity is a relationship between shear stress and rate of shear strain. So, the simulator, this is the redwood viscometer, the measuring flask, marked at 50 cc. We also have the stopwatch, the thermometer, and of course the working fluids, engine oil and glycerol. First is to click on the drop-down list to select the fluid, the engine oil first, and then click on the drop-down list to select temperature. After selecting the temperature, click on the lift button. As you can see, the flow of fluid starts. Observe the rise in level of fluid in the container and click the stop button when the fluid reaches 50 cc mark. Now click on reset button to reset the setup. It's already recorded in the table. Again, select the next temperature and repeat the procedures for all remaining temperatures. After performing the same procedure for all the readings, select the next fluid from the drop-down menu, the glycerol, and we'll just repeat the procedures for the selected fluid and various temperatures. We'll now observe the variation in kinematic viscosity with change in temperature by clicking the plot button to plot the comparative graph for both fluids. So, comparing the graph between kinematic viscosity versus temperature for both fluids, as the temperature increases, the viscosity decreases, and as the temperature decreases, the viscosity increases. Observing, therefore, we can now conclude that the viscosity is inversely proportional to the temperature.
So, for the computation of the other data, we will be determining the kinematic viscosity of a certain fluid using this formula, where kinematic viscosity is equal to A multiplied to T minus the quantity of B over T, where A is equal to 0.00246 squared centimeter over squared second, and B is equal to 1.72 squared centimeter. So for the engine oil, at a temperature of 55 degrees Celsius, having a time of 525 seconds, substituting its value to its main formula, we can generate the kinematic viscosity of 1.28822 squared centimeter over second, or equivalent to 1.29 squared centimeter over second. At a temperature of 60 degrees Celsius, substituting its value to its main formula, we can generate a result of 0.79420 squared centimeter over second, or equivalent to 0.80 squared centimeter over second. The next one is at 65 degrees Celsius, having a time of 250 seconds. We can calculate the kinematic viscosity as 0.60812 squared centimeter over second, or equivalent to 0.61 square centimeter over second. At a temperature of 70 degrees Celsius, having a time of 135 seconds, we can generate the kinematic viscosity as 0.319359259 square centimeter over second, or equivalent to 0.32 square centimeter over second. And lastly, is at a temperature of 75 degrees Celsius, having a time of 85 seconds, we can calculate the kinematic viscosity, which results to 0.197364759 square centimeter over second, or equivalent to 0.20 square centimeter over second. So for the next one, the glycerol. At a temperature of 55 degrees Celsius, having a time of 468 seconds, we can get a result of 1.147604786 square centimeter over second, or equivalent to 1.15 square centimeter over second. At 60 degrees Celsius, having a time of 330 seconds, we can generate the kinematic viscosity as 0.8065878788 square centimeter over second, or equivalent to 0.81 square centimeter over second. At a temperature of 65 degrees Celsius, having a time of 235 seconds, the kinematic viscosity calculated is equal to 0.5707808511 square centimeter over second, or equivalent to 0.57 square centimeter over second. So next one, at a temperature of 70 degrees Celsius, having a time of 118 seconds, the kinematic viscosity calculated is equal to 0.2757037288 square centimeter over second, or equivalent to 0.28 square centimeter over second. Lastly, at a temperature of 75 degrees Celsius, having a time of 81 seconds, we can generate the kinematic viscosity as 0.1780254321 square centimeter over second, or equivalent to 0.18 square centimeter over second.
Observation. This portion is intended to conclude the different parameters and variables involved in the study. Taking consideration on all factors involving the result of computation, data from simulation, and making conclusion of it will greatly help the study to be executed perfectly. So based on the calculation discussed by Engineer Antenor, this is the tabulary data for the engine oil and glycerol. With a given temperature 55, 60, 65, 70, and 75, it have different time recorded based on the simulator. While applying the formula B equals 80 minus B all over T, we have also a different computed viscosity. Based on the properties of viscosity, the higher it is, the higher consumed time flow. So the viscosity and time are directly proportional to each other, which are observable to our tabulary data. On the other hand, the relationship between temperature and viscosity have different cases. So in order to fully understand the relation of it, let's grab the computed data. This is the model graph of the two fluids used in the simulation. Blue line for engine oil, while the red one is for the glycerol. The graph between these two fluids have the same form, meaning fluid behaves with the same manner. As the temperature increases, the kinematic viscosity decreases, and vice versa, in which the temperature and viscosity are inversely proportional to each other.
For the safety reminders, first, select the appropriate liquid and temperature. Second, before collecting the fluid at a certain temperature, check whether it completely fills up to the indicator in the cup. Third, always record the readings at a stable temperature. Fourth, pay close attention to the fluid as it possibly reaches the 50 cc mark in order to avoid leakage. And last, ensure proper setting of the ball valve to avoid leakage.